let me introduce Zhijie. Zhijie is currently an associate professor at the School of Mathematics and Statistics, Fuzhou University. He is broadly interested in theoretical computer science, combinatorial optimization, and algorithm design. His recent research topics include the modular maximization and online algorithms. Okay, now let's welcome Zhijie for his talk.
Thank you for the introduction and for the invitation to this workshop. It's my great pleasure to participate in this workshop and share my recent works on optimization from structured samples. This talk is based on my two SML papers, joined with Professor Wei Chen from MSRA, also the organizer of the workshop, and Jialin Zhang and Xiaoming Shuang, my advisors from Institute of Computing Technology, Chinese Academy of Sciences. I'll begin with two classical combinatorial optimization problems. The first one is the maximum coverage problem. In this problem, the input is an unweighted bipartite graph. We need to select a most k nodes from the left side such that the number of neighbors of this set is as large as possible. The objective function is denoted by fg, also known as the coverage functions. It is well known that this problem enjoys an optimal 1 minus 1 over e approximation algorithm, and this is optimal. Like this problem, there are many combinatorial optimization problems, like set cover, min cut, max cut, minimum spanning trees, standard tree, and so on. This problem enjoys a common feature, that is they are model-driven, meaning that their input are complete. We will revisit this feature soon. Another interesting problem is inference maximization. This problem can be seen as a generalization of the maximum coverage problem. It is first proposed and studied in the context of the social networks. The social network can be modeled as a weighted directed graph. In this graph, the nodes represents the agents, and the edge represents the social relationships between two endpoints. If I have a directed edge to you, that means I have an impact on you. Besides, the larger the weight of the edge is, the larger my impact on you is. In a social network, if we release some information to an agent or a node, then the information will spread to its neighbors. For example, in this paragraph, in this graph, the information is spread toward one of its neighbors. Next, once these neighbors receive the information, he will again spread the information to his neighbors, like this, and the information will spread over and over again over the graph until the spread is ends. In this graph, the active node, the red node is called active, and the node that is receive the information initially is called the seed node. This phenomenon is called the word of mouth effect. Using this effect, the advertiser can advertise over the social network. Basically, or roughly speaking, he can select a set of nodes to release the ads. Then the ads will spread over the social network. This method is called the viral marketing. If we use the mathematical language, then we can define the information function as the following. For a given s, we use sigma s to denote its function value, meaning the active nodes, the number of active nodes if the information spread over from S. Once we define the inference function, we can define the inference maximization problem. That is, we can select at most k nodes to maximize the inference of the selected nodes. This problem is a generalization of the maximum coverage problem, and it admits an optimal 1 minus 1 over E minus epsilon approximation. And there are another algorithm other than the greedy that can run in almost linear time. So this problem was almost solved. But these two problems have a drawback. That is, in reality, the model parameters or the input are often unknown. For example, in a social network, the edge parameters are often unknown. This means because the graph is very, very large, so one cannot collect all the information about it, or because one just do not have the access to the social network. That means because the social network belongs to some social platform like Twitter or Facebook. So once we are in this situation, we cannot use the previous algorithms to solve the problem because we do not have the complete input. In this situation, nonetheless, the machine learning comes to rescue. We call it in algorithm studies, there are two common tricks. One is the optimization, the other is the machine learning. The optimization is also known as the model-driven optimization. In this type of optimization, the parameters are often known and the input is also complete. Many combinatorial problems, like the maximum coverage problem and the inference maximization problem, belongs to this type of optimization. For machine learning, the objective is very different. In this problem, the parameters is often unknown. The goal is to learn these parameters or learn the unknown functions from the samples. Theoretically, there are PAC learning model or PMAC learning model to describe these problems. Motivated by these two types of algorithm studies, it's natural to ask the following questions. That is data-driven optimization. That is, can we optimize the functions from the samples when the function values is unknown to us? This is a very interesting problem, but in the literature, it is rarely studied. Until 2017, in this stock paper, Bakansky, Rubinstein, and Sinner proposed an optimization model called optimization from samples. In this model, the input is a set of samples known as FSI. Here, SI is RID from some distribution, and the number of samples T should be polynomial in the input size. Based on these samples, one need to solve the optimization problem. For example, in the maximum coverage problem, this F should be the coverage functions, but in the inference maximization problem, this F should be the inference functions sigma. But the key point is that we only have samples to optimize this problem. One may think Now that we have some samples, we can use these samples to learn the model parameters. Once we get the models, we can use the model-driven optimization to solve the problem. So if the machine learning can be done very well and the model-driven optimization can be done well, then one may expect that the overall optimization can be done very well. This raises the following problem. That is, machine learning and plus the model-driven optimization. Whether it can solve the data-driven optimization. This is an interesting problem. And for example, for coverage functions, it is proof that it is PMAC learnable. By the way, this result is due to one of our speakers, Fuzhou. And besides, the coverage function, the maximum coverage problem admits an optimal 1 minus 1 over E approximation. So for coverage problem, the learning problem can be done very well, and the model-driven optimization can be done very well. So one may think the data-driven optimization can be done well, but the stock paper says that under the OPS model, the maximum coverage problem does not admit constant function approximations. So indeed, this framework does not work. Data-driven optimization can be very difficult. Even machine learning and model-driven optimization can be done very well. So the problem is how to bypass the limitation of OPS model. Previously, there are several approaches. This approach usually bypass the limitation by weakening the optimization objectives. For example, for general monotone submodular functions, because coverage function is a monotone submodular function. So for general monotone submodular function, no constant approximation is possible under OPS model. But if we assume additionally the function has coverage C, then it enjoys an approximation ratio regarding to C. If C is a constant, then this ratio is also a constant. This is the first work. In the second work, this neat paper, it considered inference maximization. It said that if the inference function has some community structure, then also under OPS model, this problem has a constant approximation. In the third work, we know that in OPS model, we have a set of samples with known function values. In the third work, there are another set of samples with unknown function values. We need to use the samples with known function values to find the maximum of the set of samples of unknown values. So this problem is proved to be solvable under OPS. So we can see this ray approach works bypass the limitation of OPS model by weakening the optimization objectives. Our approach is very different. Our approach is called optimization from structured samples. In our model, we still optimize the original objective functions, but instead, the samples can take additional structure information. Using these models, our contribution in a word is that the data-driven optimization is possible under our proposed OPSS model. Now I will go into details about our OPSS model. First, I will introduce the maximum coverage problem under OPSS model. We know that the input of maximum coverage problem is an unweighted bipartite graph G, and it needs to solve. It needs to optimize the coverage functions Fg by selecting at most k nodes. So, but under OPS model, the graph G is unknown. Instead, we have a set of samples Fi, Fg, Si as input. We need to use these inputs to solve the problem. In our OPS model, we called it maximum coverage from samples, aka MCS. In our model, the graph is also unknown. Instead, we have a set of samples, Si, NGSI. Here, NGSI means the neighborhood of Si. That is, we not only know the neighbors of Si, not know the number of neighbors of Si, but we also know which nodes are its neighbors. Apparently, this type of samples is structured in that it reveals some structure about the graph. We need to use these samples to solve the maximum coverage problem. And our results are as follows. First, we have an assumption for the sample distribution D. This assumption includes 3 conditions. First, let me note that the assumption is we indeed need some assumption. For example, if the distribution D always returns the empty set, then we certainly cannot do any optimization. So there must be some conditions over D, and we found 3 conditions about this distribution. First, it is feasibility, meaning that the sample S must be a feasible set. The second condition is sufficiently large sample probability, meaning that each node U can be sampled frequently. The third one is the negative correlation, meaning that the events that U is sampled are negatively correlated, meaning that if I is sampled, then the probability of U is sampled will be smaller. This is what I mean by negative correlation. Under this assumption, I have the following algorithmic results. Theorem 1, it says if the maximum coverage admits a kappa approximation, then for distributions satisfying assumption 1, MCS admits a kappa over 2 approximation. Second, for spatial distribution, namely uniform distribution, MCS problem admits a kappa minus epsilon approximation. Besides, we also have some hardness results. First is the optimality of the algorithm. It says that there exists a distribution D. It satisfies assumption 1 such that 1/2 approximation is impossible for the problem. This approximation ratio is tight because if we run the brute force algorithm for the model-driven problem, maximum coverage problem, then kappa equals to 1, and our algorithm has a approximation ratio of 1/2. So this means our algorithm is tight. Our second hardness result is the necessity of assumption 1. It means that by dropping any of the 3 conditions of assumption 1, any constant approximation is impossible for maximum coverage from samples. This is our results for the MCS problem. Now I introduce the kappa over 2 approximation algorithm for the MCS problem. Our algorithm has 3 steps. The first step is to construct a surrogate graph tiled G. This graph serves as an approximation of the original graph G. The second step is to obtain a kappa approximation set T over tiled G using model-driven optimization algorithm. And then in the final step, we do not return T directly. Instead, we return T with probability 1/2, and with the remaining probability, we return the first sample S1. I will explain why is this later. First, let us consider the first step. We see an example about it. In the first step, to construct the estimate of the neighborhood of U, we collect all SI such that U belongs to SI, and we consider the neighborhood of this SI and take an interaction of them. We use the result as an estimate of the neighborhood of U. In this example, there are 3 SIs, and only the first 2 SI contains U1. So we consider their neighborhood NGS1 and NGS2. We take intersection of them, and we get V1 and V2. We use this set as an estimate of U1's neighborhood. It's easy to see that the neighborhood belongs to the estimated neighborhood. So the original graph G is a subgraph of our estimate graph G, tiled G. This is the first step. In the second step, we know T is a kappa approximation over tiled G. So T is good enough in tiled G. But T suffers from a learning error. This is because the function value of T over tiled G equals to the real value of T and the learning error. The learning error can be very large and unavoidable. So the question is how to make up for the error. This is solved in the third step. In the final step, we show that any random sample can cover the error. This means that the error belongs to the neighborhood of S1. So with this property, we can see that S1's function value plus T's function value is larger than kappa times the optimal value. The proof sketch of step 3 is as follows. So we first observe that the error can be split into the error of each element in T. Second, so it suffices to prove that the error of the single element belongs to the neighborhood of S1 with high probability. And by union bound, we can prove what we want. Finally, we observe that another way belongs to the error must because it belongs to the intersection of SI. Since SI is IID, this means that with high probability, we will belong to SI. because it should with high probability V belongs to S1 because it should belongs to every Si and Si are IID. So this is the proof. Also, we also consider the influence function, the influence maximization under OPS model. For this problem, we first recall that for the influence maximization, the input is a weighted directed graph G. We need to optimize the influence function by selecting at most k nodes. But the influence function, we need to further define it because we need to define how the information is spread over the social network. This is defined by the diffusion model, and in this talk, we consider the independent cascade diffusion model, namely the IC model. In the IC model, before the diffusion, the weight of each edge can be interpreted as a probability, and the edge exists with this probability. And before the diffusion, we first sample the edges according to this probability and obtain the live edge graph. And if we release some information, this information will spread over the live edge graph. So the spread is like this.
Hi, hello, Zhijie. Because of the time, maybe you can just summarize the results of the inference maximization.
Okay. So this is what the spread is. So in the inference maximization from samples, this problem, the input is a set of samples that encode the spread cascade. We need to use these samples to solve the problem. And we have the following results. First, we also proposed assumption, which contains 3 conditions. And the first 2 conditions is the same as the assumption for the maximum coverage problem. But the third condition is that it's straighter. It should be a product distribution, meaning that the events that each U is sampled are independent. In this assumption, we show that IM's problem admits an O-kappa approximation. And if additionally, the parameter C equals to epsilon and smaller than 1/3, then the problem admits a kappa minus some epsilon approximation. This is our result. And we finally gave a conclusion. So there are some takeaway messages. First, we know that learnable does not imply optimizable from samples. Second, optimization from data may need structural information. Third, data-driven optimization may still be possible when learning is impossible. There are some future works. First, one can see how to relax the product distribution condition for IMS problem. Second, one can investigate other objective functions under OPSS model. And finally, one can finds a unified sample model, making data-driven optimization possible. Thanks. That's all.
Okay, thanks, Zhijie, for the nice talk. Is there any questions? Hi, Professor Liao, you can just ask your question.
Yeah. So, okay. So thanks for your great talk. Maybe I'm the last question for you. Because I also did some data-driven influence maximization under the collaboration and supervised by Dr. Wei Chen. And your theoretical results is very nice and beautiful. I would like to ask, do you consider how to apply this theoretical algorithm and models to into this real data? Do you try something about, for example, this social influence? How say this probability? How to get this real and how to verify this is really work? Do you have some idea or suggestion for me? Thank you.
Oh.
For example, you say the network inference. So how to get this inference probability? This apply the real data, real probability obtained by your algorithm. Do you have some suggestions? Thank
you. So for example, if an advertiser advertising company, if he can collect the past the history data generated by his advertisement and use this data to serve as input of our algorithm. So I think if one want to apply our algorithm, he must have some historical data. So for example, he can first he can first advertise by select the seed nodes according to the distribution satisfying, for example, assumption 2 or assumption 3. After one collect enough data from these distributions, he can use our algorithm to update his advertisement strategy.
Okay, thank you for your answer. Maybe we can discuss a bit offline. Thank you. Thank you,
Okay.
Professor Zhang.
Yeah, thanks. Any other question? If there is no further questions, let's thank Zhijie again for his talk.